This is the year 2133. Welcome to the Museum of Quantum Antiquities. Here lies every piece of quantum technology developed in the 21st century. Today, we're embarking on an adventure into a fascinating sphere of technology. A stark departure from classical computing, which relies on bits, this realm utilizes qubits. As we journey back to the dawn of the 21st century, you'll see how these cutting-edge machines, though large and shiny, heralded a new era. So buckle up, fellow explorers, here we go. First on our exhibit is the frosty realm of superconducting quantum computers. These technological titans thrive in the chilly confines of near zero kelvins. It's not because they enjoy the cold. Rather, at icy temperatures, certain materials exhibit zero electrical resistance. This phenomenon, known as superconductivity, lets qubits maintain their quantum states for longer durations, creating the possibility for more accurate computations. The calculations are performed by subjecting the qubits to controlled microwave pulses, which act as quantum gates. Intriguing, isn't it? However, keeping these qubits cool was no simple task and remains a critical area of research. Yet, major players like IBM with their quantum hummingbird and Google with their Sycamore model were not deterred. Their groundbreaking work is showcased in the gallery above. Moving on, we come to the gymnasts, trapped ion machines. These technological marvels, unlike their superconducting counterparts, exploit the attributes of individual ions to carry out complex operations. Picture an ion, a charged atom, suspended in space by electromagnetic fields. This ion, with its internal energy states, serves as our qubit. The question now arises, how do we make it work? We utilize a laser beam. The laser beam nudges the ion into a superposition of states, a unique characteristic of this advanced computation. To measure the outcome, we deploy fluorescence techniques. The ions emit photons, which are detected and read as the output. It's an elegant dance of light and matter, with ions flipping and twisting, like gymnasts under the laser's influence. If you look to your right, you will see companies like IonQ and Honeywell working with this technology. Next on the menu, we have the topological quantum computers. These aren't your typical machines. No, sir. They're like the pretzels of the quantum world, all twisted and intertwined. Topological computers use quantum states for robust and fault-tolerant operations. They employ anyons, which are exotic particles that exist in 2 dimensions and have peculiar braiding properties. Information is coded into their non-local, collective behavior. By braiding these anyons in specific patterns, we can perform operations that are fault-tolerant. Although this concept was under development in the early years of the century, it held a promise of a stable and error-resistant future. But hold on to your horses, because we are not done yet. We're moving on to the realm of light with photonic quantum computers. Instead of using physical matter, these machines use light, or more specifically, photons. Photons, just like quantum particles, can exist in a state of superposition and can be entangled. By these photons, photonic machines achieve information processing. The concept sounds as bright as the light it uses, doesn't it? Back in the day, research in Chinese universities was heavily focused on photonics, and they achieved some pretty neat feats. At the last stop of our tour, we have quantum dot computing. This was an intriguing field that was just beginning to emerge in the early part of the century. Picture this: tiny semiconductor particles, so small that they're considered these little guys are what we call quantum dots, and they behave in some truly fascinating ways thanks to principles of quantum mechanics. In this realm, these particles, these quantum dots, are used as qubits. But what them so special? Well, they allow for the manipulation of electron spin, which is a fundamental property of electrons. By manipulating these spins, they can perform computations in a similar vein as the other advanced technologies we've explored today. This was a fresh and exciting field back then, holding immense promise for the future. Now we see its potential realized in our everyday devices. This concludes our tour. Thanks for joining us on this journey through the evolution of technology. Curious and keep exploring.